Well, we're going to have an exciting journey into the wonderful world of kinematics, and this is the start of our journey. And we're going to look at position, velocity and acceleration, the cornerstones, in fact the Academy Award winners of kinematics. So without any further ado, let's have fun. No, don't say that. Come on, it is fun. So the position of a particle moving in a straight line is determined by its distance from a fixed point. Yeah, we know that. Called the origin, the RGB, okay? And whether it is to the right or to the left, yes, that's because position is the same as displacement, really, and it has to have a sign or a direction. And we're doing one direction motion in one direction. I think they call it rectilinear motion. But basically, we go plus or minus. That's the way we indicate the direction, okay? And the position is in relation to the origin. Conventionally, the direction to the right of the origin is considered to be positive, just the same as we do with numbers on a number line. So if we consider a particle which starts at the origin and begins to move, then the position of the particle P is determined by the number x. That's the way we do it, okay? If the unit is metres and if x is minus 3, that means the position would be 3 metres to the left, wouldn't it? Yes, while if x is plus 3, the position would be 3 units to the right. But you don't have to say to the left or the right, we just say minus 3 or plus 3, okay? That's its position relative to the origin. If it moved 3 units to the right, it would move plus 3 metres in this case, or if it moved 5 units to the left, it would be negative 5 metres travelled. Yes, you get that. Okay. The displacement now. The displacement is defined as the change in position, right? The change in position of the particle. Displacement is different from distance, okay, as we'll see as we go through all this. It is important, yes, to distinguish between the scalar quantity distance and the vector quantity displacement. Look at this. If we considered a particle that starts at the origin and moves firstly 5 minutes to the right to point P, and then 7 units backwards the other way to Q. Now you think about that, okay? It starts here, goes 5 that away and 7 that away, okay? Its final displacement or position measured from the origin is minus 2. However, that is its displacement. From the start, for the finished position minus starting position is minus 2, okay? However, the distance travelled is, what was it? It was basically 5 units to the right, then 7 units to the left, which was 12 units. So the displacement's minus 2 compared to where it started, and its distance is 12. So they're very different beasties. Displacement is the same as distance if the direction doesn't change, but otherwise it isn't, as in this case, where it did change direction, okay? That's very important. I hope you get that. Difference between a vector and a scalar is basically what that is, because displacement is a vector, it has a size and a direction, and distance is only a scalar, it just has a size. All right. Velocity, that's the rate of change of displacement. The velocity of a particle is defined as the rate of change of its position or displacement with respect to time. Both the average rate of change, the change in position over a period of time, and the instantaneous rate of change, which specifies the rate of change at a given instant in time, will be considered. If a particle moves from x1 to x2, time interval t1 to t2, then the average velocity is just the change in position over the change in time, without any consideration of what happens in the intervening interval, okay? It's just the final position minus the starting position over the final time minus the initial time. That is the average velocity, okay? The instantaneous rate of change of position with respect to time is the instantaneous velocity. So if the position x of the particle at time t is given as a function of t, then the velocity of the particle is determined by differentiating, finding the derivative of the rule for position with respect to time. That's very interesting and very important. So this is the average, this is the instantaneous. That's just dx dt. This is delta x over delta t is the average velocity. Please get that right. Okay, common units for velocity and speed are meters per second, centimeters per second, or kilometers per hour. But there's a big sting in the tail of all this stuff. Often they mix up units between kilometers an hour and meters per second. So I'm going to show you how to convert from one to the other. If we're going between meters per second and kilometers per hour, okay, so x meters per second equals, now let's do it. We've got meters per second times, now if I divide by 1,000, so that's 1,000 meters per kilometre, but kind of upside down, but you get that, don't you? Yes, and then you multiply that by 3,600 seconds per hour, and you will notice, ladies and gentlemen, that I hope, what am I doing here? Converting meters per second to kilometres per hour. Yes, the meters cancel out, ka-chum, ka-chum, as I'll do in a moment, and the seconds cancel out, like that. See? And you get left with kilometres per hour. And so, therefore, that is 18 over 5, or 3.6, is the conversion from meters per second to kilometres per hour. Kilometres per hour is always more than meters per second, so that's how you know how to do the conversion. You multiply by 18 over 5, or 3.6, to get from meters per second to kilometres per hour, and the other way round, that's the one we just did. And if you want to go from kilometres per hour to meters per second, you basically multiply by 5 over 18, or divide by 3.6. You have to get that. Can you remember, please? I just remember 18 over 5. That's what I do. And if I go from kilometres per hour to meters per second, I have to go down, so it's 5 over 18. If I have to go from the other way, I go the other way and go up, 18 over 5. That's from meters per second to kilometres per hour. Alright, can you please commit that to memory? Okay, now, acceleration. Well, we know what that is. That's defined as the rate of change of velocity with respect to time, and there's no real scalar equivalent to that. The scalar equivalent of distance over time is just speed, whereas displacement over time is velocity, but acceleration is just velocity over time, the rate of change of velocity. Okay, yes, that's the average acceleration would be dv, or delta v over delta t, and the instantaneous acceleration is the derivative of the velocity, or the double derivative of the displacement. Goodness, are you taking all this in? Hope so. Yes, so in kinematics we basically we express this second derivative of displacement with respect to time as x dot dot, okay? And similarly for velocity we express that, we often express that as just x dot, the dot denoting a derivative, a double dot denoting a second derivative, alright? Now there's a lot of theory there, so we better come and do some examples now and clear our heads, and you'll see how easy it is, really. Alright, what do we got? A particle is moving in a straight line so that its position x centimetres relative to the origin at time t is given by this expression. It's a cubic, and it's an upside down cubic because it's got a negative here. So we need the initial position, its position when t is 2, initial velocity when t is 2, its speed. Now speed is just the size of the velocity, okay, because speed does not have a plus or a minus, doesn't have a sign, it's just a magnitude because it's a scalar, okay, and when and where the velocity is 0. Oh, look, this looks pretty straightforward, guys. Let's get into it. A, the initial position, so therefore x at naught, you just plug naught into this this equation, and what do you get? No, it's at the origin. So the initial position is naught, e.g. the origin. Number B, what do we got? Position when t is 2, no problem. Just put 2 in there. Just substitute 2 into here, and you would get this, right? And you would get minus 2 centimetres, and that's a perfectly acceptable way to express your answer. In fact, that's the way we always do it. If you wanted to put it in a sentence, you would say it was 2 centimetres to the left of the origin, because all of this stuff is relative to the origin. Okay? Very good. What's C? Initial velocity. Well, now we've got 2. What do we got to do? Yes, we have to take the derivative of this one here. Yes, because the derivative dx dt is velocity, where x is displacement. So it'll just be 3 minus 3t squared. So we need the initial velocity. Put t is naught in there. We get 3 centimetres per second, right? That's what we get. d. Now, what's that? Velocity when t is 2. Just put 2 into that expression for velocity. This one here. And we get that, which means we're going to get, what are we going to get? Minus 9 centimetres per second. In other words, if you put that in a sentence, that means it's travelling to the left at 9 centimetres per second. Okay? Just think of a number line. You get it when you do that. Okay, initial speed. Are we doing speed now when t is 2? Okay, now, speed is the magnitude of the velocity, okay? So that's just going to be 9 centimetres per second. In other words, take this value up here and just take the plus or the minus away and just give it a number, 9 centimetres per second, all right? Very good. When and where the velocity is 0, well, okay, velocity, now what was velocity again? This thingy here, wasn't it? So we have to set that equal to 0, yes? And then when we get the time from doing that, we'll plug that back into the expression for displacement to get the where, okay? All right, that's a nice little quadratic-y, isn't it? Quadratic-y expression. So we get that, and we get that. Oh, look at that. Now, this is a bit interesting because t squared equals 1. So you would say to me, well, t is plus or minus 1. Yes, that's true mathematically, but it ain't true within the context of our question because t is only allowed to be, you see, this is time. Time can't be negative, at least not on this planet. So there you can't have minus 1. So therefore t is 1. That's the when, 1 second, if you like, or t is 1 is perfectly acceptable. Then we put that into our expression for displacement here to get the where, okay? And it's 2 centimetres. So there you go. So the velocity is 0 at 1 second where x is 2 centimetres. We've got the motion of a particle along a straight line is defined by this thing, which looks like a quadratic-y thing, where t is greater than or equal to 0, being time, where x metres is the position of the particle relative to the origin at time t. Find the average velocity of the particle in the first 3 seconds, the distance travelled by the particle in the first 3 seconds, and the average speed. Now this one, guys, this one's the one to watch. This is the booby trap, or usually it's the booby trap. Because when they ask this kind of question, usually what you find is that the direction of motion has changed within that time interval, and therefore the distance, which is what you need for average speed, is not the same as displacement because it's changed direction. So if you work it out on the basis of displacement, you would be wrong. You see, you have to. I'll show you if this one works out like that, which I suspect it will. I'll show you what to do. You've got to work out 2 separate segments of the journey. Work out their displacements from the time it initially starts till it stops to change direction. Work out the displacement of that bit. Then the second segment, when it's going in the other direction, work out the displacement for that segment, strip off the pluses or minuses, add up the 2 numbers to get a total distance, and then divide by the total time of that time interval. I will show you. It'll become clearer. Now, A, today, the average velocity is just going to be x at 3 seconds minus x at 0 seconds minus over 3 minus 0, which gets us, let's see what it gets us. X at 3 is 6 metres. X at 0 looks like 0. Therefore, we've got this. It looks like 2 metres per second. Okay, that's the average velocity. Okay, but I'll bet you anything it won't be the same as the average speed. Okay. B, let's the distance travelled. Okay, distance travelled by the particle in the first 3 seconds. Yeah, now this is the thing where we've got to watch this. The distance is not the same as the displacement if it's changed direction. So what I usually do is I get the expression for the velocity, which is 2t minus 1. Okay, in that case I've just differentiated that beastie there to get 2t minus 1. Okay, now I'll draw a little graph of that to just get clear in my mind. I always draw a velocity time graph just to get clear in my mind what's happening. And as I suspected, guys, if you look at velocity, you can see that it starts off with a velocity of minus 1. At a half a second, it's got a velocity of 0. So it's going backwards. Negative, right? Negative for the first half second from its initial starting position, which looks like it was at the origin, right? Then it's going forwards in velocity from that point onwards until we get up to 3 seconds up here. So basically this thing, you see this 0 here, this 0 means, and it's negative here and it's positive here, that's the negative velocity here below the t-axis, positive velocity here above the t-axis. That means that it's changed direction from negative down here to positive up here. So we've got to basically work out the two different displacements from 0 seconds to a half a second, and from a half a second to 3 seconds, work them out as distances then, without the pluses or minuses, then add up those two numbers to get distance. That's very important to do that. So I've basically summarised it over here as I proceed through the steps. V is negative when you go from 0 to a half second, it's moving backwards. V is 0 when t equals a half, that means it's stationary, and V is positive from a half up to 3 seconds, right? That's what we've got to do. So we need to work out those different segments of the journey as displacements, turn them into distances, and add up the two distances. So when x at t is a half, looks like it's minus a quarter, okay? Now, when t was 0, x was 0. We knew that. When t was 3, x was 6. Okay, so therefore, there's a little number line of position there. It starts off at the origin. It goes from t is 0 and x is 0. That's what happens there. It goes backwards to minus a quarter when t is a half. And then it moves forwards, as this graph indicates here, getting faster and faster, from t is a half up to t is 3, where it reaches 6 meters, okay, from the origin. So what is our distance? Well, that's representing that bit there, okay, at t is a half, x is minus a quarter, and there we have t equals 3 and x equals 6. So therefore our distance is the first bit here when it went back from the origin to minus a quarter. So that's 1/4. Take away the minus off it. It's just 1/4 of a meter. Yeah, that's in part A of the journey from here to here. Okay, from t is 0 to t is a half a second. It goes backwards to the left by 1/4 of a meter. Then in the second part of the journey from here up to 3 seconds, it basically goes from minus a quarter and it reaches its destination at 6 meters. So the second part of the journey is 6 1/4 meters, right? Therefore the total journey length is 6.5 meters, or 13 over 2 meters, which is different from the displacement over the first 3 seconds, which was just 6 meters. So you see how important it is to get a feel for what the velocity is doing with time, which is why I always draw a graph of velocity versus time. And if it crosses that horizontal axis of time during the time interval over which we've got to calculate, say, distance or average speed, then you've got to be careful, because the displacement is no longer the same as the distance, because it has changed direction, and you have to work out the two segments of the journey individually, get displacements, convert them into distances, and then just add up the two distance numbers, and you'll be right. Okay, so I hope you get that. That's the crucially important part, and this is the booby trap question, and this one as well. Both of them are basically booby trap questions, yes, when the thing changes direction. Alright, let's have another go at another one now. Average speed. Oh yes, sorry, I got all carried away. Average speed, of course, is distance over time, which will be 13 over 2, which is the distance, divided by the time, which will get us 13 over 6. 13 over 6 meters per second is average speed. That's part C, and now we have indeed finished the question. Next question. What's this? Okay, we've got a position of an object travelling in a horizontal line is x meters from the origin at t seconds. It's a quadratic one, upside down quadratic one. Sketch the position time graph showing key features. That's all right, we can do that. No problem. Let's do it. We've got to get a handle for this on this first though. That's our quadratic. T's got to be greater than or equal to 0. Take the -4 out there and you get that. Now factorising that is easy. Whole number factors will result. That's great, which would give us intercepts of t is minus 1 and plus 3. Of course, minus 1 makes no sense in the context of this situation because time has to be greater than or equal to 0, but it gives us a feel for what our graph is doing. So I'm working out the peak here, the turning point, the hump of the graph, the apex, and that'll be halfway between these intercepts. So if the intercepts are at minus 1 and plus 3, which is the case, halfway between there would be t is plus 1. When you work out x at plus 1, 12 and 8 is 20, minus 4 would be 16. So that gets us our turning point on the graph. And the other intercept, I think we've got all our information now. T is 3. So, yeah, there it goes. So, intercept there, that's right, because when t is 0, x would be 12, yes? And there's the turning point there, which I just worked out. That's it, we've done it. That's part A done. The velocity now, this is what's this. Find the velocity at time t seconds and sketch the velocity time graph. Yes, this is what I always do anyway. Yes, that's it. Well, I've done the derivative of this one. Yes, I've done the derivative of that. And there it is. Yeah, that's a graph of that, you see. So it looks like it starts off at 8. What is that? What are the units on that? It's meters per second. So that's got an intercept of 8. So it starts off at 8 meters per second. At 1 second, it's got a velocity of 0 when it changes direction into the negative. And you see that tallies with that. See, because it's going in the forward direction, which corresponds to an initial velocity of 8 meters per second. Then it decreases to 0 at 1 second. Therefore, that's the apex there. It's not going forwards anymore, and it starts to go backwards, and the displacement starts to go down. Okay, and that corresponds with a 0 value of velocity here with a maximum displacement here, and the gradient 0, because the velocity is the derivative of the displacement. Everything ties in. Isn't maths beautiful? It is truly, truly beautiful. Now, have I done everything I need to do there? Find the velocity at time t and sketch the graph. I've did it. I've done it. Very good. Excellent, guys. So let's move on to number C. Find the acceleration at time t seconds and sketch the accelerator. That's all right. Very easy, because the acceleration is a derivative of the velocity, right? So that'll just be minus 8. And that's constant at minus 8. Note the double dot there to denote the second derivative, and the dot here to denote the first derivative. That's what we do in kinematics. It's just a notational thing. Okay, we can draw that graph now. Pretty easy. It's just always minus 8. Meters per second, or meters per second squared. Now, I haven't got a speech impediment. It means that if the acceleration is minus 8 meters per second squared, it means that the velocity will change 8 meters per second to the left every second. 8 meters per second every second, or 8 meters per second. Okay? You get that? That's what it means. And you call it 8 meters per second, or 8 meters per second squared. In the negative, that is. Yep. Now, have we done everything? There we have, haven't we? Yes. All right, now D. Let's go with D. Represent the motion of the object on a number line. Yeah, okay, well, I'm just going to get a handle on the entire motion first, between 0 and 4 seconds, okay? All right. We know that that's x, that's x dot, that's x double dot. The acceleration is constant. We know that at minus 8 meters per second. The velocity is initially 8 meters per second, decreases linearly to 0 at t is 1, and that gets to, if you plug that in, that'll be, when t is 4, that'll be minus 24 meters per second. So it's going pretty fast when t is 4. We better get out of the road, guys. It'll bowl us over. So, and the displacement started at 12. That should be meters. Sorry, I'll just fix that up. Just excuse me. Abracadabra, I fixed it. I had inadvertently written centimetres, so it should be meters. Okay, so what am I saying? It's meters when t is 0, peaked at 16 meters when t is 1, which we saw on the quadratic graph on the last screen, and then decreased to 0 when t is 3, and finally minus 20 meters at t is 4. If you put 4 into there, you're going to get minus 20. Okay, so now we've got it. I think we can do a really nice number line now. Presumably they mean a distance number line or a displacement number line. So this is the origin, okay? And what did we get? That's position. That's when t is 0. That's its position, starting position. Yes, that's its peak position, or its furthermost position to the right before it turns around. Okay, at t is 1, and then it goes backwards to there to 0 at t is 3. Okay. And it gets to minus 20 meters at t is 4. Okay, so there to there. Okay, now I've written here that the v is velocity is 8 when t is 0. The velocity is 0 when t is 1. That makes sense because that's the point at which it turns around. And v is minus 16, getting faster and faster and faster. If you put in into there the velocity when t is 0. Wait a minute, t is 0. What's v? It'll be, oh yeah, that's right, if it's t is 3, you put that into there. T is 3, put that into there, you get v is minus 16, so it's going pretty fast to the left now. And there is our final position when v is minus 24. Okay, that, I think that denotes it pretty well on the number line, and the acceleration is always constant at minus 8. I just thought I'd throw that in for good measure. So acceleration is drawing the motion to the left, yes? Always to the left. Even though it started off moving to the right, the acceleration was always to the left, slowing it down, stopping it, and moving it to the left. Alright, how do you go? Do you get that all? I think it's pretty clear. Alright, so that's the end of that. That's D. Now, what are we got to do now with E? Find the displacement of the object in the third second. Okay, now to do that, you've got to find the displacement at the end of the second, and then the second, and then the end of the third second, and then find the difference in the positions, right? That's what we'll do. So when t is 2, x at 2 would be that according to our formula, which gets us that, which gets us 12. And then when t is 3, we get that with 3 substituted in now, and we get that, right. So therefore, x at 3 minus x at 2, which gets us the displacement during, so from the end of the second to the end of the third second, alright? That gets us the displacement, so it's therefore it's minus 12 meters. Okay, do you get that? That's a little bit funny, that wording, isn't it? The third second means from the end of the second, from the end of the second, which means when t is 2, till the end of the third second, which means when t is 3. Alright, now the last bit of this question. Find the distance travelled in the first 3 seconds. Alright, now that's another one of these problem questions, because we know we had our velocity time graph like this. Okay, so the distance travelled, we've got to split it up into the distance travelled from t is 0 to t is 1, and then the distance travelled from t is 1 to t is 3. Okay, so forwards that way and backwards there. Okay, so when x is 0, that is at t is 0, x is plus 12. When t is 1, x is plus 16, and that means we've moved plus 4. Then when x is t is 3, I mean, x is 0, which means we've moved 16. Now you notice I didn't say minus 16, I'm just doing distances here. Okay, it actually is a displacement of minus 16, but we are considering it the distances. That's all we want, is the distance. So that's 4 and that is 16. And therefore the distance is 20 meters. Yes, the distance is 20 meters. Now we're not going to do this example here, we'll just move to another video. Okay, so we'll do 4, 5, 6 and 7 in the next video, and I'll see you next time. Have a wonderful day and thanks for coming.